Okay, for our final video for this chapter of chemistry, we'll be examining the topic of percent composition. And this is, when we refer to percent composition, we are normally referring to the percentage by mass, okay, by the total mass, compared to the total mass of the substance in question. Don't confuse this with like molar percentage or some other thing. We're comparing amounts of mass here. It's important to keep that in the back of our minds at all times during this process. So some quick review about percentages. For this to make sense, you have to clearly understand what a percent is and what it means. Percent, remember, it means per centum, okay? The Latin out of per or out of 100. So centum is 100. Percentages are just fractional parts of some whole. I can always represent a percentage as a fraction, and I can always take a fraction and convert it into a percentage simply by performing the division that the fraction indicates. So if my fraction is 3 out of 100, that is 3%. It's 3 per centum, 3 per 100. But even if the denominator is not 100, if I divide the fraction, the numerator by the denominator, I'll still come up with a decimal, which is out of 100. Okay, if I round to the hundredths place, I'll have a equivalent fraction that is out of 100. So even non-100 denominator-based fractions will still be able to be converted to percentages rather easily. And this is what I do when I grade your papers. There is a total number of points. Let's say you had 35 points possible on a particular assignment, and you earned 30 of those points effectively. Well, you earned 30 out of 35. 30 divided by 35 is 0.86. You earned an 86% on that particular assignment. Okay, and so on. So converting fractions to percentages, it's important to keep that relationship well understood here, because that's basically what we're going to be doing in most of these cases where we're asked to analyze the percent composition of something in chemistry. So in chemistry, percent composition by mass is a representation of how much mass a certain element, a particular element, contributes to the total mass of the compound subject or substance. Okay, just like here in this example of grades or points, there's a total number of points which you can earn, and then there's an actual number of points that you actually did earn. And that fraction is the relationship which is going to establish the percentage. It's the same thing here in chemistry, except we're not talking about points out of a total number of points. We're talking about how much mass one particular element's mass out of the total mass of that compound contributes to the total. What percentage of the total does it make up? So for example, if a compound is 68% oxygen by mass, okay, 68% of its mass comes from the oxygen element, then for every 100 grams of that compound that I have, or 100 any mass unit really, doesn't have to be grams, then 68 of those are going to be from oxygen. Okay, the oxygen is going to take up 68 grams out of that 100 grams. It is 68% of that total mass. And let's say it's 24% hydrogen. So the percentage of mass is due to the hydrogen atom's contribution to the total mass is 24 grams out of 100. And if I'm analyzing all of the elements in a compound, this must always add up to 100%, because the total mass, if I add up all of the masses of the individual components, then I better get exactly the same amount of mass for the compound as a whole. Okay, again, this is just your basic law of first law of thermodynamics, the law of conservation of mass energy. This mass cannot be created or destroyed. It's not coming from out of nowhere. We're not producing extra mass. It's either there or it's not. And it's coming from these elements, or it has to be coming from something else. So if I have all the elements involved and I add up all of their masses, or the percentages of all of their masses, it has to equal 100%. So let's say I know two of the elements are oxygen and hydrogen. Well, if I add those, that only gets me to 92%. together. So 92% of the mass is coming from those two, which means that some percentage left has to be coming from everything else. And I can find this, and some problems will ask you to do something like this, find the percentage of, the nitrogen or whatever is left in the compound in addition to those original elements. I can find that simply by subtracting this total of the ones that I know from 100. So 100 minus 92 would mean that this X in this case has to be 8%. So if it's nitrogen as the remaining element, then 8% of the mass is coming from the nitrogen. Okay, so the basics of this are pretty simple, and it's mostly things that we already know, and it's review. But how can we use this? Well, let's go back to one of the problems that we looked at in finding the empirical formulas. In fact, we can turn this into a percent composition problem instead. So we had this chemical sample of some compound. We don't know what it is. We found that it's so much of it is aluminum by mass, so much of it is sulfur by mass, so much of it is oxygen by mass. So what is the percent? Instead of asking what is the empirical formula of the substance, we're going to ask what is the percent composition and again, the percent composition is going to be however much that element contributes out of the total. So we need to know the total mass of this compound as a whole before we can calculate the percentages for each of these. So the total is going to be this much aluminum plus this much sulfur plus this much oxygen. When I add all three of those together, okay, I won't go through this in detail, but just trust me, you can do it yourself if you don't believe it. It comes out to be 30 grams is the total mass of this compound, which we discovered before is actually aluminum sulfate. Okay, but that's not really relevant to the problem at this point. Total mass is 30 grams, and we know that 4.73 of those, 4.731 grams of those are aluminum, from aluminum. So there is the fraction that I need to come up with the percentage of the mass that comes from the aluminum in this compound. Okay, so when I divide this fraction, turn it into a decimal, I get 0.1577, which means that 15.77% of this compound's mass is coming from aluminum. Okay, again, we're going to just be careful to keep in mind here, we're talking about the percentage of mass, not the percentage of like numbers of elements compared to each other. It doesn't mean that there are 15 aluminums for every however many oxygens. It means that the mass is 15%. The sulfur, we had 8.433 grams of sulfur in this compound out of a total of 30. So that means the sulfur is going to contribute 0.2811 or 28.11% sulfur. So 28, just over 28% of the mass of this compound is coming from the sulfur atoms. And then finally, the oxygen is the big one here. In fact, the oxygen contributes 16.836 of the grams out of the 30 total grams in the compound, which is a percentage of 0.5612 or 56.12%. Okay, and so we've determined the percent composition. This thing is 15.77% aluminum by mass, 28.11% sulfur by mass, and 56.12% oxygen by mass. If I'm not sure if I've done this correctly, I can check. I can add these values up and see if they add to 100%. If they do, it's a good sign. It's not a guarantee that I've done everything right, but it's a pretty good indicator that I'm on the right track. Okay, and in fact, if I add these up, 8 and 2 is 10. 9, I get 10 here also. Carry a 1, 6, 14, 20. So carry 2, 4, 5, and 10. And indeed, I get 100% in fact when I add these values. So that's a good indication that I've done this problem correctly. Okay, this is how it can be done if you're given various masses to start with. Let's look at the example of the aspirin problem that we worked yesterday as well. So if I have 100 grams of aspirin, well, I've already been given my total here. We've said that in this problem, we're analyzing 100 grams of aspirin. So that's my total mass. And of that 100 grams, 60 grams is carbon, 4.480 grams is hydrogen, and 35.53 grams is oxygen. Well, actually, in this case, since I'm going out of 100, the fractions are really easy, and I won't even need a calculator for this. Because since percent is out of 100, and I'm operating actually out of 100 here, these percentages are going to be very simple. 60 parts out of 100 is 60%. 4.480 parts out of 100 is 4.480%. 35.53 grams out of 100 is going to give me 35.53% of the mass. And again, if I check these, if I add these up, it will add to 100 or very, very close to it. Okay, if you're off by a couple hundredths or so, it doesn't really matter. Again, that's just coming from the measurement imprecision or the measurement inaccuracy, measuring errors. So if I'm operating out of 100, it's very simple. Okay, so I have 60% carbon in aspirin by mass. 4.48% of the mass of aspirin is from hydrogen, and 35.53% of the mass of aspirin is from oxygen. Okay, let's take a slightly different approach here. Let's combine the two ideas of percent composition and finding the empirical formula. So we're not going to cheat. We already know this is the problem that we just worked with aluminum sulfate, but we're going to pretend we don't know any of that. And we're starting with just this information. We know that there's some compound that is 15.77% aluminum by mass, 28.11% sulfur by mass, and 56.12% oxygen by mass. How do I find the empirical formula based on this? Well, there's a difficulty here. Because remember, the empirical formula is going to require molar ratios. And these are percentages of mass. They're not even masses yet. They're just percentages of mass. So I need to convert these into actual masses. And then convert those masses into moles to find the molar ratio. And again, that's what's going to give me the empirical formula, is that molar ratio. So if I have 15.77% aluminum, that means out of every 100 grams of aluminum, or excuse me, out of every 100 grams of this compound, if I had 100 grams of it, 15.77 of those would be aluminum. So this is a little bit tricky, but I can actually just do this. I can just say, well, let's assume then that I have 15.77 grams of aluminum. Let's assume that's how much I have. And I can do this because no matter whether I actually have 100 grams of this substance, aluminum sulfate, as a whole or not, 15.77% of it will still be aluminum, 28% will be sulfur, 56% will be oxygen. And the ratio between these is going to be the same whether I'm basing it on a 100 gram sample or a 200 gram sample or a 113 gram sample. The ratios will be the same. And that's what I'm ultimately looking for here, is the molar ratio between these things. So I can pull this trick where I just assume, okay, well, it doesn't tell me how much the total is, but I'll just assume that it's 100 because that'll make the numbers easy to work with. So if I have 100 grams then of aluminum sulfate, I will have 15.77 grams of aluminum, and I will have 28.11 grams of sulfur, and I will have 56.12 grams of oxygen. And now I can take those amounts and I can perform my molar conversion to come up with the molar ratios on them. So again, aluminum is, what was this, 26.98, I think. Sulfur is 32.06. Oxygen again is 16. And we won't get the same exact numbers here as we did when we found the empirical formula before. We're not going to get these 0.1754, 0.2630, 1.052 values because we're starting with different amounts. But the ratio between these values that we got before and the ratio between these should be the same. So we should end at the end of the day with the same empirical formula. Let's see if it works. Okay, and we're back. Performing the mole conversions, we get this molar ratio between these three elements, 0.5845 moles of aluminum for 0.8768 moles of sulfur for 3.508 moles of oxygen. And these numbers, again, they look quite different from the numbers that we got before. But from here, you're going to find that it's going to become the same. Again, I'm going to divide all of these by the smallest value so that I get a whole number of 1, for at least for the aluminum. And these values come out to be 1, 1.5, or very close to 1.5, and just over 6, which is exactly the same ratio that we got when we did this before. 1 to 1.499, 1.5, and 5.997 to 6. So I come up with the same ratio, the same molar ratio, which means that the empirical formula will be the same. Again, I just need to eliminate this fractional value, multiply this by 2, and again I get 2 to 3 to 12, just as we did before. Okay, so that is sufficient for examples for now. Again, obviously we'll work some of these for homework and we'll see if you're grasping it or not. Again, please don't hesitate to contact me with questions. I'll be more than happy to help explain anything in greater detail.